What you can see here in front of you is the website of Deep Soil version 7.0, which is the software that you can download for free. It was created by Joseph Hassash and his team by the University of Illinois. And this software, as I explained in the lecture, is normally used for calculating 1D ground response analysis. It can be based on the use of analytical tools or analytic analysis based on linear analysis, equivalent linear analysis, and non-linear analysis. The practice that I'm going to show in this session is to do more with linear analysis and equivalent linear analysis, even though you can also try and practice with non-linear analysis if you feel that you are confident after reading enough about the topic. In this website, you can see that there are different versions of Deep Soil. I do recommend you to download the latest one, which is 7.0. And here you can click on the manual, which is really useful, and you can start reading if you want to get more info, more indications of how to use the software. And the installer is here. So if you click on that one, it should download directly. For using the software, the only thing that you need to provide in this case is your student email, and you need to create a profile. So it's relatively easy to use. I just want to quickly show you the manual provided by Deep Soil, in this case the version 7. There's a manual with each one of the versions that you can find in the website. But the truth is that I will go for the latest one, given that Deep Soil is not, it does not require a high capacity and performance of your computer. So you will see that even with a very low RAM memory computer, you can use the software in any way or in any form. Very quickly, I'm going to show you about the table of contents. So the manual is self-explanatory in itself. So each one of the sections or parts that I have explained about ground response analysis, and also lecture 2 about seismology and the transmission of seismic waves, you will find many of those concepts here in the manual. So it will ring the bell when you see some of those, and I will even invite you to compare them with the definitions that I showed you before. About the table of contents, I would say that the manual really starts from page 21, and there are a series of concepts and aspects related to, for example, the representation of the seismic waves in terms of velocity, displacement, and acceleration that you can find here. Area's intensity, if you remember, was associated with the intensity or the amount of energy released by an earthquake and the duration of that earthquake. Then when you move on to analysis flow, it's going to explain you step by step how the software works and how you can undertake any exercise. It will do it like in a very basic way by explaining like the most fundamental aspects of each one of the sections. And 3.6 is to do with the results. So it will explain what is each one of the graphs that you can see there showing. Some of them you might recognize them, some of them you might find them difficult to understand, but the truth is that they are explained one by one in this case. You know about time history, you know about stress strain behavior, the hysteretic loop of the associated with the dynamic properties of the soil, spectral plots, you also know them. Maybe displacement animation or mobilized strength is new to you, so that's why I recommend you to take a look at them and see how they work and how they function. The fourth section of this of the manual is to do with the soil models, and those soil models are needed for defining the nonlinear behavior of the soil. So you will find some models to define the backbone curve. If you remember, it's that initial curve at the beginning that reaches the maximum point and then reloads. So then you'll have one for that backbone curve, and then you will have another one for the hysteretic behavior. So it will be a load and reload of the of the cyclic behavior of the soil. And that's the reason why there are so many models present here, because depending on the type of soil that you have, depending on the conditions of the soil, if it is saturated, you will need to also design the model in such a way that it follows the rules of those kind of soil behavior. So in this case, this is a section that I am not going to ask you even to read. Well, if you want to read it and you want to know more about it, it's entirely up to you. But this is not something that we are going to ask or to cover for the part of ground response analysis, because it's too advanced at this stage and it will take a long time, even just to really get a grasp of what it will mean to define some of these models. If you wanted to know more about dynamic soil behavior and you wanted to try with your own models, I mean, it's entirely up to you, because this takes a bit of time. So just for your information, that you have access to those models and how they work here. At the end, you can find some extra material about randomization of site profile properties that you can also obtain from the software, and something that I find quite useful and essential in this case is the examples and tutorials that have been provided by the group of investigation, and they go from the very simple one, which is the undamped linear analysis with resonance, corresponding to the first transfer function that I explained, to a non-linear analysis in examples 6 to 14. So these examples are again also self-explanatory, because it takes you step by step throughout the analysis and the calculations of the software, and I do recommend you at least to try with the first 4. What I'll try to do in the next slides is to show you how it works, example 1, 2, 3, and maybe 4 too, and you could practice yourselves to see if you get the same results. So this is what the software will look like. What I wanted to do before even trying with one of the examples was to show you the user profile of deep soil. And I'm sure that you have used much more complex software and computational or analytical tools in the past. So I must say that deep soil is one of the easiest software to use in an initial stage. So let's say just by intuitively decide which action to take, because as you can see, there are not many windows or many actions to click on. I will say that there are the typical ones here at the top. So file, input, summary, convert units. So normally I will go for metric instead of English units. You have options, which will give you to basic aspects about the configuration of the software, more with doing with the use of the analytical tool. So these are the 3 options that you can see here. Those are the 3 main options that you will need to use in order to perform an analysis of any type. Here, if you click on analysis, you will have new profile or open profile, because you can save your own profiles and continue from them. But if you click on new profile, this is what it shows. So again, very simple, very straightforward, nothing difficult at all, at least to click on the essential options. So when you look at analysis method, there are 3, and those correspond to the 3 that I explained in the lecture. You have linear analysis, equivalent linear analysis, and non-linear analysis. If you remember, linear analysis will correspond to the 4 transfer functions that I covered, going from the homogeneous layer with undamped properties on a rigid bedrock to a layer soil with damp properties on an elastic bedrock. So linear covers quite a lot of options in this regard. Equivalent linear I also explained at the end of the lecture, and if you remember, equivalent linear was more to do with that step beyond, where you will adapt the non-linearity of the soil by doing a series of iteration of for changing the shear modulus and the damping ratio with the shear deformation. Still is in between linear and non-linear analysis, and non-linear analysis would correspond to those nonlinear soil behavior models that I showed before for the case of the manual, that I do only recommend you to use if you feel comfortable and you've read enough about the use of those kind of models. But still, you must know that they are available in this case. Again, deep soil is only for 1D problems, so you are going to have a soil profile with different layers, straight soil layers, one beneath the other one, where you can also add a water table on top of the soil profile, but there wouldn't be any option to create the soil or ground soil or soil profile. So just for you to bear in mind before you start with the exercise. So if you click, for example, on linear, it will show solution type. Okay. The transfer functions correspond to the frequency domain analysis. I barely explain anything about time domain analysis because it will be a different type of analysis, well, in this case, solution type associated with the analysis method. But you could also click on time domain and compare it with the frequency domain to see the differences. I would say that if you want to follow the transfer functions and most of the explanations found in books, frequency domain for the linear analysis is the most adequate solution type. So if you click on that one, you will see that here it doesn't show anything because these options are associated with the analysis method of nonlinear analysis. You can also see automatic profile generation. I say it off because I want to create it myself. Unit system, I will go for metric unless you prefer going for the English unit system. I will say that in this case we are going to use the international unit system with meters, seconds, and kilonewtons per cubic meter. And the software also gives you the option of using other equivalent analysis apart from the linear analysis. In this case, really it's not giving you the option of doing something else apart from the equivalent linear analysis. But if, for example, you click on no, so it's not showing it. Only if you click, for example, on nonlinear analysis, it will tell you if you want to get an equivalent linear analysis or no. Yeah, that happens because when you try to create a nonlinear analysis, sometimes, as I explained in class or in the lecture, you want to compare it with a, let's say, less complex system or method of analysis, such as equivalent linear. So it would be recommendable to compare equivalent linear with nonlinear analysis. But let's go back to the linear analysis. For now, you know everything you need to understand at this stage for creating that linear model. But before we get into the analysis, I'm going to move on to the motion section. So in this part, the second tab of the software, which is known as motions, is going to show you different type of earthquakes. In this case, the time motions and the characteristics, if you can call it in a way, of these earthquakes or seismic motions. You can also introduce some. So if you click on add new motion, you can actually choose a file and you can introduce the information here manually. I've done it in the past. It's relatively easy. For that, the only thing that you need to do is to copy and paste the information of an Excel spreadsheet into this window. So it's as I said, relatively easy to do, and it's entirely up to you if you want to use new seismic motions. But imagine that we click on a typical input motion, such as the case of Chichi earthquake in Taiwan. As you can see, first of all, what we find is the acceleration time history, acceleration with respect to g, or as a factor of g, and time at the bottom. So this could be the axis of time. You have velocity time histories, displacement time histories, and then you have RS intensity and Hauser intensity. The RS intensity, I explained it in class in lecture 2, which will represent the amount of energy, the total amount of energy from 0 to 100 produced or released by the earthquake. And if you remember, we will say that the duration of the earthquake will go from 5%, or in this case 0.05 of the RS intensity, to 0.95 or 95% of the energy. So this is the basic information about our seismic motion, and this is the first step before even trying to calculate any kind of of linear analysis. From there, what the software does, and this was also undertaken by Seismo Signal, if you remember, it was to transform the input series of the motion into frequency domain. For that, what it actions the software is to change from time domain to frequency domain, and that's why the Fourier amplitude is shown here. As you can see, the Fourier amplitude represents g per second with respect to frequency or period, and you can change that here if you say shift between period and frequency. So this one will be the frequency domain representation of that earthquake to know what are the main earthquakes, or in this case, what are the main frequencies that the seismic motion is characterized by. At the bottom of that one, what it shows you is something that you are aware of, and it's the response spectra, the spectral acceleration. In this case, with a 5% damped spectral acceleration, I believe that you can change the amount of damping ratio of that spectral acceleration. But this will be a very useful tool, as you have probably seen for the case of a Seismo Signal, and is that this graph here at the bottom right will represent the period, or the different zones within the periods of a single degree of freedom system subjected to these time histories or this seismic motion, where it will be more damaging or more dangerous. As we can see, is in this range between 0.078 to maybe to 3 seconds. So you've practiced this before. You can see that deep soil performs the same kind of transformation from time domain to frequency domain, and then the spectral acceleration, which is very useful as part of the first steps of the analysis of any kind of ground response analysis. So yeah, you have it there too. The last tab of the software could be the profile tab. And in this one, you can click in any of the examples that have been explained previously in the manual. So imagine that you read about an example of the manual that you want to practice yourselves and want to know more about. You see and you know that you have all the information here. So you will just need to double click here, or say click on one of the examples, as in an open profile, and it will take you directly into the profile that you have. So you just need to click on next, and it will take you here to the soil profile. I'm going to start top with this recording, and I'm going to continue about how to move from here to the following steps of the analysis for undertaking one of these exercises. Without getting into a specific example yet at this stage, I just want to go back to the analysis tab, which was the first one that you had here at the top left. And what I intend to do in this case is to move on to the next step if we wanted to perform one analysis. So if we've clicked on new profile and you've selected linear analysis frequency domain, as I said before, metric as the unit system for the automatic profile generation, you are ready to continue into the analysis section, and for that you need to click on here on next at the bottom right. Once you click there, it's going to take you to stage 2. So if you see here, we've completed step 1, and now we are on step 2, and it is showing it as if it was in this yellow section. So you could go easily onto step 1 by clicking. You cannot click here, but you have to click on back here at the bottom left of the window. So it takes you to something that it may look a bit more complex, but I want you to just think or realize that the part that we are mainly interested in is going to be here. So there are 2 tabs here at the top: layer properties and advanced table view, and I'm going to go through each one of them. Before we move on to that, I want to show you what I mean with 1D analysis, and it's exactly this. Imagine that the soil surface was located here. What the software is asking us at this stage is, what are the soil layers that are above this bedrock? Because this bedrock will represent, as explained in the lecture, all that section that goes beneath, or in this case underneath, the superficial soil layers, any kind of clay, sand, or any kind of soil layer that you locate between the soil surface and the bedrock. And what the software is asking is, can you define the different soil layers at the top of that bedrock until it reaches the soil surface? So what we will do is add depth. So we are literally including soil layers with certain depth here. But there's no two dimension. It is entirely one dimension, and everything is analyzed as if it was a simple column such as this one, where we place straight layers on top of each other. If you go to an advanced table view, what we can do in this case, and I do recommend you to do it, is to literally create your soil profile. So imagine that you created 10 meters of a soil layer. Look at what is happening. It represents the bedrock at the bottom, as it will happen in real life, and the soil layer is created above that. It is true that this is not a realistic and accurate representation, because the bedrock will be a total of kilometers underneath that soil layer that we've created. But we don't mind. I mean, we just want to see that the bedrock is there, and then we'll define afterwards if the bedrock is rigid or elastic. Then after the depth of the soil layer, or in this case the first soil layer, is asking us about the unit weight. If you remember, the unit weight is a multiplication of density times the gravity. So in this case, by creating the unit weight, what we are adding into the system is literally we are saying to the system that we know the density of our soil. So instead of asking the density, it's asking for the unit weight, which is more appropriate for the design or the site investigation of a soil. So mind that I said 20 kilonewtons per cubic meter, and you can see how much is that in kilograms per cubic meter if you did the comparison. And then you have another value that you are familiar with, which is the shear wave velocity. So remember, if we have the shear wave velocity and we have the density of our soil, we will be able to calculate the shear modulus. And that's the reason why you're not going to see here the tab asking for the shear modulus, is that the software is directly calculating the shear modulus. So imagine that in this case the shear wave velocity was something like 250 meters per second. The last thing that we need to add into the soil profile could be the damping ratio. So in this case, given that we have selected the linear soil model, the D minimum is going to represent the constant value of the damping ratio for that soil profile. So imagine that we wanted our soil to be completely undamped. What we will do is to add 0% of damping ratio in this case. If we wanted to add a 5% of damping ratio for the soil, we will include 5 there. Okay, so again, this is the basic information for a linear analysis, and what you need to add into the system always could be thickness, density, or unit weight. In this case, unit weight will be obtained from the density of the soil, shear wave velocity, and from these two you can calculate the shear modulus, or vice versa, and the damping ratio, the constant value of the damping ratio. As you can see here, if you clicked on a different soil model, so it could be MKC or a different type of soil model, different factors will show up that you need to complete. As you can see, this can get much more complex, and that's not the intention of this activity or this exercise. It's more to show you how the software works. But if you want to start with only the linear analysis, this is exactly what you need to do, and these are the sections that you need to complete. Now, imagine that you wanted to add another layer. You have to come here at the bottom of the soil profile and you say add one layer. So if you added one layer, what we will do is to add another layer beneath, or in this case below the selection of the layer 1, but on top of the bedrock. So another layer with 20 kilonewtons per meter, but with a higher shear wave velocity, which implies that the soil is stiffer, and maybe 10 of damping ratio. So what we will have is 2 different soil layers on top of the bedrock, and we want to calculate either the stresses and the strains in each one of the soil layer, or we want to calculate acceleration, velocity, and displacement on top of each other. So you can see here that you can add as many soil layers as you want. and it's entirely up to you how you want to define them in terms of soil properties. When you go back here to the section of layer properties, what it's telling you is can you define one by one each one of the properties of the layers? As you can see here, what is showing is exactly the values that we have included before. So you could either do it here manually, or you could do it in the advanced table view. So it gives you the option of choosing either of the two of them. But to define the case of the bedrock, you need to click here on the bedrock. So if I click on layer 1, it shows this information. If I click on layer 2, it shows this information. I can also change the layer name. So maybe I can say Mexico City Clay. Then when you click on the bedrock, it's going to show this information. And it's entirely up to you how you define the bedrock, depending obviously on the type of analysis that you undertake. If you remember, the type of analysis of the transform function for linear analysis 1 and 2 will be with a rigid half space. So rigid bedrock, you need to click on here on rigid half space. And if you click on rigid half space, as you can see here, everything is blocked. So there's nothing that you need to add in this case, because we assume that all the waves are going to be contained within the soil layers here. So the wave is coming from underneath the bedrock, passing through soil layer 2 and 1, and it's going to be contained here, and there's not going to be any type of wave scattering or wave dissipation. But if you click on the elastic bedrock, you need to define the bedrock. So for that, it's going to ask you for the same properties: shear wave velocity, unit weight, and damping ratio. And actually, if you look up for the information about elastic bedrocks, you will see that there's loads of information about different soil properties that we can add to an elastic bedrock. The inclusion of these properties into the bedrock, what is going to result is in a reduction of the maximum acceleration on top of the surface, because of dissipation of part of the energy into bedrock when the shear wave is going back to that elastic bedrock. So these are the first step, as you can see here, to define the soil profile. It may look a bit difficult at the beginning, but as you can see, for the case of the linear analysis, is not more complicated than adding the soil properties of each one of the soil layers that you want to calculate, and from there you can move on to step 3, 4, and 5 of the analysis. I will continue in the next slide, and I can separate a bit each one of the video recording. Imagine that we are back to the soil profile definition. Before I show you how to create or how to introduce the soil properties of a soil layer, and in this case what I'm going to do is just simply select one soil layer with some soil properties: 10 meters of thickness, 20 kilonewtons per cubic meter of unit weight, 250 meters per second of shear wave velocity, and 0% of damping ratio. So I'm going to define the soil layer to be undamped. Into layer properties, I click on bedrock and I choose the rigid bedrock. Something I forgot to say before is that you want to include the water table at the top of the layer. So what it will mean is that the water table has been created here on top of the soil surface. If there were different soil layers, you could even say that the water table is contained within or between two different soil layers. But in this case, we are going to define the soil layer to be completely dry. So it's not under saturated conditions, so we are talking about non-saturated conditions. Now, to proceed with the next step, what we need to do is to click on check data here at the bottom right. And I'm going to click there, and this is what it shows. The first step before even just creating the interaction between the soil profile and the seismic wave is to recognize the information that we have included into the user profile. So it's showing the shear wave velocity with the depth, maximum frequency, so in this case is providing the natural frequency of the soil that has been automatically calculated. We could do it by hand, knowing that we have certain shear wave velocity and the depth of the soil. And the natural period of the soil profile has also been determined in this case. By now, if you had one soil profile, you will be able to calculate this manually by hand. So you can even compare the results obtained with deep soil with your own hand calculations. But then this could be just a mere representation of the information that you added before. If you had different soil layers, what it would happen is that these lines would change the trend. So maybe they will change the shear wave velocity because other soil layers are characterized by a lower shear wave velocity, and the same applies to the rest of the properties that you can see here. So if we click on next, it's taking us to the input motion selection. So what the software is asking us in this case is to pick up one motion, one type of motion, and from there, what the software will do will obviously carry out the ground response analysis by creating the interaction between the soil profile and the seismic motion. In this case, all these motions are seismic motions, but it is also true that you could create your own, for example, harmonic loading, periodic loading, by adding a new motion where it will represent the typical sinusoidal motion. But in this case, I'm just going to do it in the most realistic way, which will be to introduce one type of earthquake, Chichi earthquake, for example, the one that I explained before. Again, all the information that I presented at the beginning of this presentation is included again. So this is just showing what the time histories for the Chichi earthquake are, for the Fourier amplitude in terms of frequency domain and the spectral acceleration. And in this case, what we need to do is to continue from here. I mean, it's telling us, the software, this is the input motion that you want to apply to your soil profile, and afterwards you will see what happens with the signal. So if we want to continue, this is step 3. As you can see here, we are still in a step 3. To proceed with the ground response analysis, we need to click next again, and it's taking us to this step 5. Okay, so in this step 5, normally the step 4 could be when you have different type of soil profiles and with the water content, so it's skipping directly the step 4, and it's taking us to this step 5. If you are doing or carrying out the linear analysis, I will say that you don't need to consider these two aspects at the beginning. But if you were doing an equivalent linear analysis, if you remember, the effective shear strain ratio will depend on the magnitude of the earthquake, but by default is 65% of the maximum shear strain, and the number of iterations could be necessary for the equivalent linear analysis. So normally I would say to put between 10 and 20. For the complex shear modulus formulation, the recommended is that we say that the shear modulus is frequency independent. There are other options that you can read more about this in Kramer's book, so I will say to go by the default one, the recommended one. And for the time domain, if instead of doing a frequency domain, you perform a time domain solution, here is included some information that, again, it will require more time for you to process and to understand, but just for you to know that it exists and that you can click on there. Given that our analysis is frequency domain linear analysis, we are not going to use this information for now. In terms of the output settings, or what the software is going to use, we can define, if we had different layers, what we want the software to show. In mind that there's one soil layers that we are not very interested in, we could unclick, and we just, for example, click on the one at the surface of the ground soil. But again, this option is going to be more useful when you have different soil layers. So let's say that we have maintained things as they are by default, because we consider that our analysis is too simple at this stage and it does not require more thought. We click on Analyze, and that last click is going to take us to the analysis of the ground response analysis that I've explained in lecture 4, and that this software is useful for calculating 1D problems. So if we click on Analyze, it might take a bit of time, but normally for examples like this one where we have only one soil profile, it shouldn't take more than a few seconds. Something something is quite how to say, is quite remarkable when we look at the graphs. We see the acceleration is showing the relative velocity, showing the relative displacement and RS intensity. These values correspond to the values at the top of the surface. Okay, so these resultant values are the values that we will obtain on top of our soil profile if the soil profile was characterized by the geotechnical properties that we added at the beginning. Do you see something weird here? We are reaching values of above 2 billion g of acceleration. I mean, that's quite significant. It's quite dramatic, and I would say that any type of structure will collapse. So in a way, what the software is telling us is that we've reached the resonance phenomenon. If you remember, I've added a damping ratio of 0, so it's undamp conditions, and that's the reason why we reach this stage. So what the software is telling us in a way is that the acceleration, velocity, and displacement are too high for the soil profile to withstand it, and that's why we obtain this. As you can see here, there are a series of tabs. First of all, time history plots, which is this one here. If we go on to stress strain plots, this is what it's showing us. The shear stress will represent the deformation and the stress experienced by the soil. As you can see here, it's not possible to distinguish even the lines because of that resonance phenomenon. And the graph that you can see here on the right, this should ring the bell, because this corresponds to the graph of deformation versus stress versus deformation of the cycle behavior explained in lecture 3. Do you see that we have a completely straight line? That's because there are not damping properties, and in this case, all the energy that is being applied in this case is not being dissipated. So that's why it is represented by this straight line, and that's proper of a soil that has no damping properties. And again, this is unrealistic. If we had some damping, what will happen is that this graph will show a hysteretic loop of different breadth. If we move on to spectral plots, what this section is showing us is something quite useful, and you're going to recognize some of the different graphs. First of all, is showing the spectral acceleration. So the spectral acceleration, what is literally showing us is what happens with that. Well, in this case, it would be what happens with any type of single degree of freedom system applied on top of the surface of the soil that we have created. In this case, we have added it is a 5% of damping spectral acceleration. I believe that you can change that value. I just need to double check how you can do that. But in a first calculation, what it's telling us is that most of the energy, or let's say the most like the highest acceleration is shown in the range between 0.1 and probably 0.5 of natural period. This value will probably correspond to the value of the natural period of the soil. And given that the soil has non-damping properties, what is showing us is like a very significant value there, which represents that the system is under resonance. So this is a confirmation of something that is being shown by the time histories, but in this case represented in terms of a spectral acceleration. This graph that you can see here at the bottom right is the Fourier amplitude ratio. And that Fourier amplitude ratio is nothing but the representation of the transfer function between the top surface and the top of the bedrock. This is literally the calculations that we will do by hand if we follow the procedure of the transfer function for a soil layer with a homogeneous properties and damp soil properties on a rigid bedrock. So this graph that is showing here at the bottom right is literally representing that calculation that I showed you in lecture 4 of the module. The Fourier amplitude is the resultant Fourier amplitude in frequency domain of the time histories on top of the soil surface. So this Fourier amplitude is not the same Fourier amplitude than the one shown before for the case of the seismic motion of the Chichi earthquake. This could be the spectral plots. I think that's the most important tab of this analysis process, because it's giving you quite a lot of information, given that once you have the Fourier amplitude, as you can see here, you could calculate actually the values of the acceleration on top of the soil surface by doing it by hand. If you had this transfer function, you could apply the transfer function to the input motion and you will obtain actually the results obtained in the time history here. So that Fourier amplitude is what is taking us to these values of the acceleration. If you go to tab 4, is showing the profile plots. So it's showing you how the peak ground acceleration changes with the depth. In this case, we have a unique soil profile, so that's not going to move. Peak ground displacements, maximum strain, maximum stress ratio. These values are a bit more advanced at this stage, but still it is useful to know that you can access them there. The next tab is the mobilized strength, so you can see how much is the shear strength that is being reached at the soil profile. Displacement and minimation, if you click on that one, it will show you how the soil profile is going to change, or how much is going to displace as a consequence of the input motion applied to the soil. Obviously, we're talking about a soil that is under resonant conditions, so the displacement is going to be huge, and that's because we are talking about undamp soil properties, and this is not realistic. I mean, obviously we will be talking about the failure of the soil and any type of superstructure that was applied or placed on top of that soil profile. Next up, again, is giving us the response spectra summary. But in this case, what it's giving us is the representation of the different soil layers. So in this case, since we only have one type of soil layer, is telling us the layer 1. But in mind that we had different soil layers, what the program will do is the spectral acceleration for the different soil layers to compare how much the signal will be amplified between the different soil layers. The software is also giving us the option, and this is very useful here at the bottom, and you will use it at some point, to export the information to other software. In this case, if you click on export to Excel, what you could do is actually obtain all those results from the different tabs here at the top into an Excel, and you can use that information for your own benefit. So everything can be exported to other platforms. Check convergence is nothing but the type that is used to tell you if, for example, the analysis that you have undertaken is accurate enough. For the case of the linear analysis, we shouldn't be using this option. For the case of equivalent linear analysis, this could be useful from the point of view that this will tell you if the number of iterations that you have used before are sufficient for undertaking the exercise, or maybe they are insufficient and you need to add more iterations. But as you can see, this is relatively intuitive at the beginning when you have a linear analysis, and it's giving you some information that at this stage you could access and you could analyze yourself based on the information that we have with the different examples of the manual, and some other exercises that I will ask you to complete for the tutorial of this session and for the summative assessment as well. What I'm going to do in the next slide is to try with 1 or 2 examples, and you have a reference there for your own calculations. What I'm going to try to do from now on until the end of this presentation, corresponding to the use of the software DeepSoil, is to go one by one for the first 4 examples. So in this case, example 1 is going to be related to the case of the transfer function 1 that I explained in lecture 4, of the homogeneous soil layer with undamped properties on a rigid bedrock. And that's, let's say, roughly represented in this picture that we have here, the figure 7.1, where the soil has 20 meters of depth with 20 kilonewtons per cubic meter of unit weight, 500 meters per second of shear wave velocity, which could represent a high shear modulus. Remember that you can obtain the shear modulus from these 2 values, and damping properties are going to be equal to 0. And we need to choose a rigid bedrock for this first case, and that will entail that the shear waves are going to be contained here and they won't be rebounded back to the bedrock. So if we go to the profile section and you click on example 1A and say open profile, what it's going to take you is literally to the example 1A. So you don't need to go one by one adding the formula or the properties of the soil. If I ask you to obviously undertake a different exercise, you will have to do this exercise by introducing different values. But in this case, just as a mere comparison exercise, or as a way of showing how it works, these simple exercises, I just recommend you to go through the examples provided by the software. So if we click on next, it's going to take us to the soil profile definition, as I explained before. And in this case, already the values of the soil properties have been included. And if we click on bedrock, rigid bedrock has been chosen, so we don't need to add any other information in there. Water table at top of the layer has been chosen, but that's not going to change in this case the results obtained with the software. If we click on check data, we are getting to the next part of the analysis, and as we can see, the natural frequency and the natural period of that soil is the same that the one that I explained in the previous slide. For this case, what we are going to choose is the seismic motion of Chichi earthquake in Taiwan, and we have all the graphs that I explained in the previous slides. When we click on next, it's taking us to this analysis control definition. As you can see here, number of iterations for the equivalent for the linear analysis array is 1. Effective shear strain is being chosen as 0.65. We don't need that one. Frequency independent for the shear modulus formulation, and everything is as it was before. Clicking on analyze is going to provide the answer for the different sections of the analysis in time history, stress and strain plots, and the rest of them. As you can see, the results are very, very similar to the ones provided before, and that is because, again, the soil is undamped, and we are reaching values of strain and stress which are dramatically high, and the soil wouldn't be able to withstand. So this is just to show you how it works and how to get into example 1A of deep soil. Important is the damp spectral acceleration. We reach the resonance point at the natural period of the soil, which is around 0.2 of natural period. If this was in frequency, it would be 6.25, and the Fourier amplitude ratio between the top surface and the bottom of the bedrock is exactly the same than shown in the previous slide. This is a good way of comparing the results with the next example, where instead of having the rigid bedrock, we will have the elastic bedrock. So for that, you need to click on the next slide. Moving on to the example 2 provided by Deep Soil Manual in page 94, as you can see there, out of 170. In this case, the main difference compared to the previous example is that instead of having the rigid bedrock, we have the elastic bedrock, and that means that instead of the shear wave passing through the layer of the soil layer and being retained here in the soil, in the main soil layer that we have the soil profile defined to, the wave could be rebounded, or it will rebound back to the bedrock. So there will be part of energy dissipation as a consequence of that, which is known as another type of damping, radiation damping. So in essence, what we will have to see afterwards is that instead of having such a dramatic increase of the acceleration at the top of the soil surface, there should be a reduction in the maximum acceleration, velocity, and displacement with this option. Moving on to the software, if we click on example 2A and we say open profile, it's going to take us to the example 2A. Analysis method linear, frequency domain for the solution type, of metric, and the same than before for the type of analysis. We click on analyze. We have the soil layer, which is 20 meters, 20 kilonewtons per cubic meter of unit weight, 500 meters per second of shear wave velocity, and the bedrock. This is the main difference with the previous example, is that we have a very stiff bedrock, which is represented by that 760 meters per second of shear wave velocity, and we could calculate the value of G from these two components, from the unit weight and from the shear wave velocity. And another factor is that a damping ratio of 2% has been included, so it will imply, in this case, it will lead to a reduction of the surface motion, because we say that by that 2% of damping ratio, part of the energy is going to be released when it goes back to the bedrock. So that's the main difference between rigid half space or bedrock and elastic bedrock. So let's move on to check data. As you can see, there's been a difference here in the soil profile definition, and the plot that is showing is that we have a shear wave velocity of 500 for the case of the layer 1, but the bedrock increases that value to this point, 700, as mentioned before, and there are like some slight differences in the profile that is shown. For the case of the soil profile metrics, as we can see them here at the bottom, they haven't changed because we still have one soil layer with a natural frequency of 6.25 and a natural period of 0.16. So the soil profile is exactly the same, and that's the reason why the natural frequency and the natural period are the same. Clicking on next, and we choose again the seismic motion of Chi-Chi earthquake. We need to, what we say with this is that we apply the Chi-Chi earthquake at the top of the bedrock, goes through the soil profile, and it reaches the soil surface, and we want to see what are the consequences in terms of acceleration, velocity, and displacement afterwards. For the analysis control definition, there's not been any change, so everything has been maintained in the same way, given that we just follow the linear analysis and not the equivalent linear and non-linear analysis at this stage. Final step, analyze. When we click on analyze, what we get is the next. So there is a significant difference compared to the previous plot that we obtained with undamp properties, since still we have damp and damped properties for the case of the soil layer, but the difference is that the bedrock is elastic, so there's been some dissipation of the energy by going back to the bedrock. And as you can see, we don't see that dramatic value of acceleration over 2 billion G, which was unrealistic. We see that the acceleration time histories, velocity and displacement is a bit more realistic, and this could be the value that will be recorded on top of the soil surface after there's been the interaction between the seismic wave and the soil profile. So you can now understand that having an elastic bedrock will dissipate quite a lot of energy, and it wouldn't lead to the resonance phenomenon that we've seen before. Still, we can see values of 0.2 G, which are high enough for any type of amplification of the signal, but it looks a bit more realistic and a bit more adequate for the analysis that we are looking for regarding certain geotechnical and specific design of structures. Strain plots, we can see that the shear strain has been represented here. So this is the deformation suffered by the soil surface as a consequence of the Chi-Chi earthquake. We can see the shear stress ratio, and here there's a representation of the shear stress versus shear strain, which will represent the hysteretic loop of this, where we will obtain in other occasion or in a different way the G value, the shear modulus of the soil, and the damping ratio. Again, you can see that the line is completely strained. There is no hysteretic loop, there's no breadth, and that's because the damping associated with the soil profile is 0. So there's not been any kind of dissipation of the energy. When we move on to the spectral plots, we can see that still there is an increase of the acceleration at certain periods. So imagine that we said that it will be between 0.2 and 1. That would be that buildings between 2 and 10 stories will be more affected if they were placed on top of this soil surface, and they will reach values of acceleration of 0.55, which is relatively high, not as high as before, which reached obviously the resonance phenomenon, and that was impossible to support. But in this case, it represents a bit more realistic spectral acceleration. For the case of the Fourier amplitude, we can see that we obtain some transfer functions. So this is again the ratio between the surface and the input motion. So if we applied and multiplied those values by the acceleration of the input motion, we will get the time history that we can see here on top of the surface. So we can see that still Those peak values that you see there, where there could be probably a value higher than 1, those take place at the natural frequency, and this is the fundamental natural frequency, and this frequency that you can see there are also other natural frequencies, but at higher cycles of frequencies. Fourier amplitude could represent the frequency domain analysis of the time histories on top of the soil surface. Profile plots, nothing to say about this, nothing to say about that. Displacement animation, what it represents is how much the soil will be displaced as a consequence of the application of this Chichi earthquake, and how much obviously the top of the soil surface could be displaced. It is saying that at the end of this animation it will go to minus 0.008 meters to the left and 0.004 meters to the right. So we are talking about something like between 4 and 8 millimeters, which is a bit more realistic, something that is being more observed in real life under seismic conditions. And the truth is that condition of having an elastic bedrock is more appropriate. So it would be very difficult to find entirely rigid bedrocks where part of the energy is not being released when going back to the bedrock, to the top of the bedrock. Response spectral summary. I want to show you this as the last graph, because what it represents is the difference in the spectral acceleration between the input motion. So what will happen if we placed a single degree of freedom system on top of the bedrock, and what will happen if we placed a single degree of freedom system on top of the soil surface. What this is telling us is that the signal is being amplified. So there's been an amplification of the signal by comparing the top of the soil surface, which is the blue line, and comparing the top of the bedrock, which is the black line. So at certain periods, such as this one, the amplification is being higher, and that's because this part corresponds to the natural frequency, or the natural period in this case, of the soil profile, and that's the reason why there's been an amplification between the input motion and the soil surface. So very useful tab, the response spectra summary. And if you had different layers, what you could see is if there's been amplification, or even the amplification of the signal at different parts of the soil profile. Third example of the software, or provided by the manual of the software DeepSoil, which is a damp linear analysis with elastic bedrock. This should ring the bell, or it should remind you to something that we've seen before, which is the transfer function 3 in lecture 4. And it's that situation where we have a homogeneous layer, single layer on top of the bedrock, with elastic characteristics of the bedrock and damp properties for the soil layer. As we can see, we maintain the same properties for the soil placed on top of the bedrock, with the difference that the damping is 5% instead of 0 that we had before. We are moving towards a more realistic interpretation of the soil behavior. Still, we are talking about linear analysis, so it cannot be an accurate representation of that dynamic behavior of the soil, because there's not been any change in the values of the shear wave velocity or the damping ratio with the deformation. And that's an assumption. I mean, that's a simplification of the reality. If we wanted to go one step forward, will be with equivalent linear analysis that I'm going to explain in the next example, or in the following step, or in the last step, could be with a non-linear analysis with constitutive models that will require quite a lot of time and understanding from your side. But it is available in DeepSoil, and you could undertake that exercise if you wanted to. Moving on to the software, we are going to try with example 3a. So we say open profile, and we see that the analysis method is the same, solution type is the same. This has been maintained in the same way. Nothing has changed in this regard. The main difference is going to be that when we click on layer 1, or we go to advanced table view, the D minimum, the minimum value of the damping ratio in this case is going to be constant, is equal to 5%. For the case of the bedrock, the values of the elastic bedrock have been maintained. And if you remember in the previous example, in example 2, the change from the rigid bedrock past the analysis and the results from a very resonant condition to a condition where the energy had been significantly dissipated because of that radiation damping, and we could see values of acceleration, velocity, and displacement at the top of the soil surface more adequate for what we will see in real site conditions. So now with the 5% of damping ratio, we are going to see a more attenuated signal, and that if we compare the values of the response spectra between this and the previous two examples, we will see a reduction, a decay in the value of the spectral acceleration. When we click on check data, in this case, nothing has changed but the small strain damping ratio. So we are saying that the soil profile is characterized by 5% of damping ratio, and moving on to 2% when it goes down to the bedrock. Natural frequency and natural period of the soil profile are exactly the same, because we have the same soil profile in terms of shear wave velocity and depth. For the case of the input motion selection, we click on Chichi earthquake. We have the same values of the characteristics of the earthquake, so nothing has changed in this case. And for the analysis control, more or less the same. Nothing has been modified, because we have the same type of analysis and the same type of solution, which is going to be based on frequency domain instead of time domain analysis. Clicking on analyze, it's going to give us several values that we've evaluated and reviewed before. We have the time histories, we have the relative velocity, displacement, and iris intensity. In terms of acceleration, we still see that we reach values of 0.2 g, and that will mean, or that will be because the transfer function is still very high at the frequency, at the natural frequency of the soil, and still is reaching very high values when it gets to the natural frequency of the motion and the natural frequency of the soil are relatively the same at certain frequencies. When we click here on the stress strain plots, we have that. I was saying before, sorry if I cut the recording. I was saying before that the values of the time histories reach more or less the same peak values, and the value in this case of the shear stress and shear strain might be a bit lower than for the previous case. The only way of really knowing that would be comparing the two cases, where we have 0% damping ratio for the case of the soil profile that we had here, and 5%. Something that I need to correct in this case is that we don't see the loop with the damping ratio here, because it's not showing the shear stress. It's showing the shear stress ratio, which is the division between shear and effective vertical stress. So that's the reason why we are always going to see this straight line for the analysis of stress strain plots, and it doesn't correspond to the analysis that we'll see for the case of the dynamic soil properties. But still, you could calculate the dynamic soil properties if you further analyzed these graphs. For the case of the spectral plots, it may look very similar to the previous case in terms of the maximum values that we get for the spectral acceleration. But it's true that if you compare the Fourier amplitude ratio between the top of the soil surface and the input motion of the two examples, we can see here that there's a reduction with higher natural frequencies. The circular natural frequency, the fundamental one, which is with n is equal to 0, is still high, and that's the reason why the spectral acceleration is still very high in that natural period of the soil. Profile plots, mobilized strength, displacement animation is very similar to the one before. And when we compare the damped spectral acceleration between the input motion and the soil layer, we can still see that even with that 5% of damping, there's been an amplification of the signal, mainly around the natural period of the soil. So in a way, what this is telling us is that the elastic bedrock is having more impact in the attenuation of the motion when it reaches the soil surface than actually that change between 0 and 5% of damping ratio. Maybe we will need a damping ratio of 10, 20, or 30% to see a proper reduction or a dissipation of the energy and a reduction in the amplification of the signal. It's going to be impossible, if not very difficult, to see that this value is going to be below the input motion, because we always say that when there's the transmission between the superficial soil layers, there's normally an amplification. So the idea would be to minimize that amplification by obviously using different type of geotechnical infrastructure or wave scattering dissipation. But the plan or the objective or the ideal situation or condition would be that this amplification is reduced to the minimum between the input motion and the soil surface layer. Last example that I really want you to focus on from the manual of deep soil is the example 4, because after this it will be mainly focused on the nonlinear analysis, which I think that is too advanced at this stage, and that will take quite a lot of time. So example 4 is to do with equivalent linear analysis with discrete points. So in this case, we maintain the same properties than before. So we say that the unit weight is going to be 20 kilonewtons per cubic meter, a shear wave velocity of 500 meters per second, and I assume that in this case the damping ratio is going to change with the shear deformation. So the discrete points are going to be necessary for creating the graphs of G and damping ratio versus shear deformation, and that's the main quality of the equivalent linear analysis, is that the values of the shear modulus and the damping ratio are not constant with the deformation. But for that, we need to create our own graph, and I'm going to show you how it works. The bedrock has been maintained as an elastic bedrock because it's a bit more realistic and it's going to attenuate and dissipate part of the energy. Otherwise, it wouldn't be feasible and logical from the point of view of the analysis. When we move on to the solver and we click on profile for equivalent linear analysis and we say open profile, there is a slight difference in the analysis method. Instead of clicking on linear analysis, we will click on equivalent linear analysis. Solution type is going to be frequency domain, and for the soil model we will have to define discrete points. Okay. There are other type of models that you could use, but for that you will need to know the factors and the different elements to define them, and that's not the case at this stage because it takes a bit of time. So I will say discrete points. So in this way you will be able to create your own G and damping ratio versus shear deformation. Automatic profile generation of unit system metric. We click on next and we have the next. We have soil layer and the bedrock, and when we click on advanced table view, we can see that the properties are exactly the same than before. The minimum is going to be 5%, but for the case of the bedrock, the properties have been maintained as we had in the previous 3 examples. 760 meters per second of shear wave velocity, 25 kilonewtons per cubic meter of unit weight, and 2% of damping ratio. When we go to layer 1 of the soil properties, there's a new table, which is the discrete points data. What is showing here is a representation of the ratio between G and G max, and a representation of the damping ratio with points of the shear deformation. In this case, the example is only giving 2 of them, but you could create as many as you want. So you could add more and more points to the graph of the change of the nonlinearity soil behavior of the soil. In this case, it has only put 2, and it says that the ratio between G and G max is exactly 1. So when we focus on the right side of the picture of the window, we can see that G versus G max is exactly the same, is constant. Damping ratio is 5%, so it does not move, and the shear strength, we don't need to worry about this now. But the truth is that we can create as many points as we want, and actually what I'm going to do is to create another example after this example where I introduce more discrete points. But just to let you know that you could create the nonlinearity of nonlinear behavior of the soil based on this table of discrete points data, and obviously with equivalent linear analysis we're talking about a more realistic behavior of the soil, not as realistic as the nonlinear, but still a more realistic design. When we say check data, we have the soil profile definition the same way. Natural frequency, natural period have been maintained because of the soil properties, and we click on Chichi earthquake to maintain the same analysis than before. We click on next, we see that there's a slight difference here, is that the number of iterations has been increased to 15, and it's because for the equivalent linear analysis we need to add some iterations to double check what I explained in lecture 4, and is that the values of G and damping ratio correspond to the values of the effective shear strength definition, which in this case has been maintained at 65%. If you knew that the magnitude of your earthquake is higher, you will need to increase the value. If you knew that the magnitude of the earthquake is lower, you will have to reduce that value. Frequency independent, and the rest of them are the same than before. When we look at the results in terms of acceleration, velocity, or displacement, we can see that the values are very similar to the ones that we had before, if not the same. And it's because when we have introduced those discrete points, you could see that we haven't really created a non-linear behavior that changes with the shear deformation. That was only to show you how it works. For creating a more realistic behavior, we'll have to see that S curve for both damping ratio and shear deformation with and shear modulus with the shear deformation. So the results that we are going to obtain here are very similar, if not the same to the ones provided in example 3 of this presentation. But it was more to show you how it works. For the check convergence, this is different compared to the linear analysis, and is because if we had different layers, what the check convergence will tell us is if the iteration or the number of iterations selected for the equivalent linear analysis is sufficient for getting an accurate representation of the nonlinear behavior. At this stage, since we only have one soil profile, one soil layer, it does not carry out that analysis. So yeah, that's it until now about the examples provided by Deep Soil in the manual. If you want to know more about them, there are plenty of tutorials actually online on YouTube that you could follow. But after example 4 is all to do with nonlinear analysis, and I think that is maybe too advanced at this stage. So for the last example, like example 5, what I'm going to show you is how to create that nonlinear behavior to carry out with equivalent linear analysis by adding different discrete points to change the soil behavior with the shear deformation. This last example, example 5, is going to be using the example 4 from Deep Soil, but changing the soil model provided for the analysis of the ground response analysis, or the interaction between the seismic waves and the soil profile. So in terms of analysis type definition, we choose again equivalent linear. For the solution type, is going to be frequency domain. We have not used time domain in this module, and it's because it will require a bit more analysis and the use of different equations, but we just focus on the transfer functions and the frequency domain equations that have been adopted until now. For the default soil model, again, we will choose discrete points because we want to create our own soil model for the equivalent linear analysis. And the profile generation is going to be off, unit system metric as always. So we click on next. This is all the same than in example 4, but what I want to do is to create a nonlinear behavior for undertaking that iterative analysis that will correspond to the equivalent linear analysis, which is the intermediate analysis between linear and non-linear. And for that, I'm going to create 1, 2, 3, 4, 5, 6, 7 points for you to see what it will look like. Okay, so for that, what I'm going to add is different points of the G versus G max, so the ratio, or the shear modulus degradation ratio. Okay, we have another one there. This one is another one. And in this case, what we have is 3. Yep, so that's in percentage. Remember, that's a difference instead of like just absolute values. Okay, so as you can see here, what I'm saying is that the formation goes from very small strains to very large strain. I mean, 100% strain wouldn't be possible to withstand by any type of soil. Normally, it will range between 0.0001 and 10%, but I've added that extra point because this soil model that I've included here, or I'm trying to introduce in this case, corresponds to the exercise that I'm going to explain in class today on Tuesday 16th of February that you will have to calculate manually. So in that way you will be able to define the values of G versus G max and damping ratio with the shear deformation and include them into deep soil. For the case of the damping, I'm going to use Darren Daly's damping calculation. So we have 2%, 2% in that case, 2.02, we have 2.16, 3.43, we have 10% there, and we have 18.2. So the main change I'm going to make in this case will be this 2% of minimum damping ratio, because in this case for the very small strain we have a 2%, so it wouldn't make sense that I put 5% when the damping ratio is 2% at very small strains. I don't know if you see here on the right of the window that the two dynamic soil properties look a bit more to the graphs that you've seen in lecture 3, which is the modulus curve reduction, G versus G max, and damping ratio with respect to the shear strain, which is the deformation of the soil. In this case, as you can see, there is a degradation, there is a reduction in the soil stiffness with the degradation, and there is an increase of the damping capacity, of the energy dissipation capacity of the soil with the deformation. And this could be probably the most realistic nonlinear soil behavior that you can add to deep soil at this stage, unless you wanted to use a constitutive nonlinear model. But what the equivalent linear analysis is going to do is that if the iterative process shows a value of shear strain between 0.1 and 10%, there's going to be a lower value of the soil stiffness, and it's going to introduce a higher energy dissipation. So if we click on check data, in this case the values for the soil profile definition are relatively the same, so that doesn't change. And when we click on input motion selection, we choose again Chichi earthquake, so that's exactly the same that in the previous 4 examples. For the case of the analysis control definition, for the equivalent linear analysis, we said that 15 iterations could be enough, and effective shear strain ratio is going to be 65% of the maximum shear strain. That's entirely up to you based on the magnitude of the earthquake. So that's part of this analysis control definition. Frequency independent for the complex shear modulus, and the rest is going to be maintained as it was. When we click on the analysis, the results obtained are probably going to be relatively the same, and that's because the values of the input motion added to that soil are not too high. So in this case, it could be good to do a comparison between linear analysis and equivalent linear analysis, because we will find out that actually with a single homogeneous layer, the two types of analysis provide a relatively similar result. Maybe in the spectral acceleration there are natural periods that are slightly different, but the fact that the two of them, the linear analysis and equivalent linear analysis, gave the same results could mean that actually in that case the linear analysis is good enough for representing the soil behavior under certain seismic conditions. If the seismic motion is subjects the soil to a very high deformation, then what we will find is that actually that linear analysis is not enough for representing the behavior of the soil, and we will require equivalent linear analysis. In terms of the response spectra, we can see that still there is an amplification of the soil. So again, the fact that we use equivalent linear analysis doesn't mean that always is going to be more accurate, and in cases like this one where we are using a simple homogeneous soil layer, maybe the two of them give the same results. One way of knowing that is to know the shear strain at which the soil is being subjected as a consequence of that seismic motion. As you can see here, the maximum deformation experienced by the soil will be around 0.008% of the shear strength. If you remember that graph of the shear modulus versus deformation and damping ratio, would change at let's say medium to high shear strengths. So let's say that by the input of this seismic motion, the Chichi earthquake, the properties of G and damping ratio do not really are not altered or modified as a consequence of this seismic motion. So that's the reason why equivalent linear analysis and linear analysis are going to be the same. But careful, because if we had a seismic motion that triggers in this case very high strains, and that could happen with maybe low stiff soils, then the equivalent linear analysis could be a more realistic and more adequate representation of the soil behavior and the ground response analysis. I want to just finish this presentation by saying that I'm going to add a couple of exercises for you to complete with deep soil as part of your own homework, and that would be the practice obviously for the summative assessment, because I will ask you to maybe undertake linear analysis and equivalent linear analysis of homogeneous layer and layers with maybe 2 and 3 layers to see how the soil behavior changes and what is the amplification of the signal in terms of acceleration, velocity and displacement on top as a consequence of that interaction between seismic waves and the soil profile. So thank you for listening to the presentation, and I hope that it's been useful by providing some overall view of the use of this software deep soil that you can find, as I said before, extra information online on YouTube, and there are plenty of tutorials that you can follow if you want to continue getting more characteristics or more configuration about the use of the computational software. As part of the homework, what I'm asking you to do in this case with exercise 1 is that with the use of deep soil, carry out the linear analysis of a soil profile characterized by the following soil properties. So in this case, these are real data based on some experimental investigation that I conducted a couple of years ago. Yeah. So the soil layer could be mainly latent butcher sand with a depth of 40 meters between the soil surface to the moment when we reach the bedrock. Shear wave velocity is equal to 225 meters per second, and from there and the density you can calculate the maximum shear modulus. In this case the density is 1.64 grams per cubic centimeter, and what I'm asking you to do there is to calculate the unit weight based on the density. You can do it by transforming some units and multiplying it by G, the gravity, and then the minimum value of the damping ratio is 0.63%. This is all the information that you need to use and to add to the software in order to carry out the linear analysis. What I'm asking you to do is to choose a seismic motion. COVID will be a good one because it has high, in this case it will subject the soil to high strains, and you can see what happens when comparing it with the equivalent linear analysis, and analyze the interaction with the soil profile. Sorry for that. Provide results in time history series and response spectral acceleration. That's what I want you to do, to compare the final results observed at the soil surface with respect to the values of the input motion at the top of the bedrock. For exercise 2, what I want you to attempt is to try with equivalent linear analysis. For that, all the information of the soil profile characterized by the properties of the latent butcher sand is going to be maintained. The exercise asking the same, that you carry out the ground response analysis based on the interaction between a seismic motion and the soil profile. And the main difference is that for the equivalent linear analysis you will need to introduce discrete points, and I've included you here a series of shear deformation and the degradation in the shear modulus and the damping ratio. Those results were obtained from using both resonance column test and cyclotriaxial testing in the lab at Edinburgh Napier University. So these are real results, and they are probably the most accurate results to represent the nonlinear behavior of the soil. Still, we are using equivalent linear analysis, so it wouldn't be the most accurate dynamic nonlinear soil behavior, but still it could be better than the use of the simple linear analysis, and that's what I'm going to ask you to do in exercise 3. So the purpose of exercise 3 will be to use deep soil and by means of undertaking the linear and equivalent linear analysis, and based on the information collected before from each one of the two exercises. So that's why I recommend you to save the profiles and save the results and then export them into Excel. Calculate velocity, displacement, and acceleration time histories for each one of the analysis, response spectra at the soil surface compared to the input motion, and then calculate maximum shear strain and shear strain experienced by the soil, and see the difference between linear analysis and equivalent linear analysis. And if you find any, reflect upon them and tell me what are the main differences and what do you extract from that. I think that this is the most advanced exercise that you're going to see probably in the module of geotechnical earthquake engineering, at least for this first part, because it combines many aspects. It combines the introduction of dynamic soil properties, ground response analysis, seismic waves. So this is a real exercise that will be adopted by geotechnical engineers for the design of buildings, because once we know the amplification of the signal at the soil surface, we can then define and design the building to be earthquake proof by obviously changing the materials and changing the conditions of the structure. So again, very useful exercise. So I hope that you can attempt doing it, and if you have any question, we can cover it in class next week in session 5 or 6, because something like this is going to be also asked for the summative assessment, and it will have a high grade associated with it, because I consider this to be a very useful exercise, very practical, and which combines many different aspects and knowledge as acquired throughout the module content.